Hello and welcome to Math 153. Welcome to Calculus 3. So when I begin these videos, I'm always going to begin with a list of things that you should be able to do by the time you have finished learning today's material. Now, these so-called learning objectives are basically a study guide in disguise. For example, by the end of today, we should be able to identify the hypothesis and the conclusion of a mathematical theorem. We should be able to determine logically valid and invalid uses of theorems and definitions, and we should be able to use theorems and definitions to write logically valid mathematical arguments. So when the time comes for me to prepare a homework assignment or to write a test for y'all, what I'm going to do is I'm going to go back and say, okay, I wanted them to be able to identify the hypothesis and conclusion of a mathematical theorem, so I'm going to write the following question. Here is the theorem, identify the hypothesis, identify the conclusion. So each one of these learning objectives is an exam question in disguise, and you can review these as you're preparing for tests. The goal for this video is to take a step back from the nitty-gritty of just the average everyday calculations and start to talk a little bit about arguing a fact from a mathematical point of view. Not just getting the right answer, but writing something that will convince even a skeptic that your answer is correct. After all, if you're right and nobody believes you, what good is it really? Now, this course 153 consists of two parts. One half sequences and series, and the other half vectors. This first half is the one where we're really going to have to be good at arguing mathematically, at writing mathematical persuasive essays in some sense, where it will be important not just to get the right answer, but also to persuade someone, even a skeptic, that the answer is correct. The second half goes more into this, typical mathematical process of calculating results, calculating numbers and answers. And this is going to be really important if you're planning to take, for example, Calculus 4, Math 254. So to get started on mathematical arguments, we have three main tools at our disposal when we're writing a mathematical argument. We have mathematical calculations, things like adding and subtracting, multiplying, dividing, integrating, and taking the derivative. We can use definitions in our arguments, and we can use theorems in our arguments. So what I would like to talk about today is how to use each one of these techniques appropriately when we're convincing someone that the answer that we have obtained is the correct one. Now, mathematical calculations you're probably familiar with. This is what's usually referred to when someone asks you to show your work. Show me the mathematical calculations that you did in order to calculate this answer. If your calculations are all correct, then your answer is probably also correct. So that's one way to convince the reader that your answer is the right one. But as we get into the sequences and series part of the course, we're going to have to rely a little bit more heavily, not just on mathematical calculations, but on definitions and theorems. Let's start by talking about what a definition is, mathematically speaking, and how to use one appropriately to convince someone that your answer is right. Now, definitions have a basic structure. There's some term, there's some word that you're trying to define, and there is some property that is satisfied by every object that could be considered that term. Term being defined is an object possessing some property. For a simple example, someone would say an even number. An even number. This is the term that they're trying to define. What property must be satisfied in order for a number to be considered even? An even number is an integer, a whole number, so no fractions, no decimals, is an integer that can be written as 2 times some other integer. Let's call it 2 times k, where k is an integer. So the term that we're trying to define is the word even number, and the property that must be satisfied in order for a number to be even is that it has to be able to be written as 2 times some other whole number. The beautiful thing about definitions is that they can be used in 2 different ways. Two-sided is what I call them. If property is satisfied, if your number can be written as 2k, where k is an integer, then the object that you're working with does deserve to be called by this term. It is even. But not only that, if the property that you're working with is not satisfied, you know for sure that the object that you're dealing with is not this term that you're working with. If your number cannot be written as 2k, then your number is definitely not even. So this definitions are two-sided. They can be used when property is true, and they can be used when property is not true. To give you a quick example, let's use the definition of an even number to classify each of the following objects as either an even number or not an even number. So for example, we have the number 3. We can say for sure that 3 is not an even number because 3 is equal to 2 times, not an integer, but 3 is equal to 2 times 1.5. But 1.5 is not an integer. It's not a whole number. So because the property is not satisfied, we can say for sure that 3 is not even. Three is not an even number. Now, looking at 2, 2 can be expressed as 2 times 1, and 1 is an integer. So the property is satisfied. So 2 is even. Now 2.5 is not itself an integer. And the definition of even number said that an even number is an integer that can be written as 2 times some other integer. But since 2.5 is not an integer in the first place, 2.5 is not even. The property is not satisfied, and therefore 2.5 is not even. So definitions can be used to make these 2 different types of conclusions. They can be used to say, my object is even, my object is not even. They can be used in both situations. Now let's practice using a definition and using mathematical calculations to write a persuasive mathematical argument for the following fact. The fact is this: if you take the square of an even number, the result is also an even number. So for example, 2 is even, you square it, you get 4, still even. 4 is even, you square it, and you get 16, and that is still even. we're going to try and write an argument that shows that that tendency is true not just for 2 and for 4, but for any even number. If you square it, the result will also be even. So here is my argument. Here is my persuasive essay to convince even a skeptic that this statement is true. Now, we cannot use just a list of examples. If we try to persuade the skeptic using just a list of examples, they're always going to have something to say to us. If we show them that 2 squared is 4, and 4 squared is 16, and 6 squared is 36, they're going to say, okay, well, what about 8 squared? What about 10 squared? What about 12 squared? And no matter how many examples you give this skeptic, the skeptic will always give you an example of an even number whose calculation you haven't considered yet. You can go all the way up to 1 million squared, and the skeptic will say, what about 1,000,002? So we need to write an argument which will cover every single possible even number in one shot. So I'm going to say, I'll just call it A. Let A stand for any imaginable even number. Okay, Mr. Skeptic, if you want A to be 1,000,002, we'll let A be 1,000,002. If we want A to be -6, A can be -6. But no matter what, if A is an even number, the definition of even number kicks in. If A is an even number, then by the definition, A must be expressible as 2 times some integer. This is by the definition of even number. So this statement holds true regardless of whether A is equal to -4 or whether A is equal to 1,000,002. So now let's square this completely arbitrarily chosen even number. A squared is equal to 2k quantity squared, which can be simplified as 2 squared, so 4k squared, which can be rewritten as factor out a 2, and that leaves behind 2k squared. If we take 2k squared, that's also going to be an integer. It's going to be a whole number still. And because this is an integer, by definition, A squared is even. The evenness property is satisfied, and therefore A squared must definitely be an even number, regardless of what you had in mind when we first considered an even number A, whether it was -4 or whether it was 1,000,002. And that concludes the argument. Now, definitions are two-sided objects. You can use them to make positive conclusions, an object is even, and you can use them to make negative conclusions, an object is not even. But theorems, our third and final tool creating a mathematical argument, theorems are a little bit more restrictive and can't be used in quite so many circumstances. Now, theorems, like definitions, come in a basic structure. If a condition is satisfied, condition A, then something else must be true as a consequence. Condition B must also be true. Now, this condition A, the one that comes after the word if, is usually given the term the hypothesis. The hypothesis is the condition that must be satisfied in order to even unlock the theorem so that it can be used. Condition B, the one after the word then, one that gives us the result of the theorem. the information that we get as a result of applying the theorem. So let's do some simple examples of theorems, and let's start with a really basic real-world one. Here is a theorem for you. If it is raining, then the street is wet. If it is raining, then the street is wet. So the hypothesis in this case, the condition that must be satisfied in order for us to even consider this theorem, is it is raining. And in that situation, if that is true, then one can make the conclusion that the street's going to be wet. Let's do a mathematical example from our calculus days. Here's one that we had. If f of x is an antiderivative of a function little f of x, then the definite integral from a to b of little f can be calculated by taking the difference of the antiderivative outputs at those limits. In this case, the hypothesis, the situation that we need in order to use this theorem, is that capital F of x is an antiderivative of lowercase f of x. Here's our hypothesis. And what we can conclude from that, if we are in that situation, then we can conclude that this is a viable technique to calculate the value of this definite integral. Hypothesis after the word if, and then the conclusion, usually after the word then. Now, not all theorems will come to you in this exact format. You may have to do a little bit of paraphrasing. So for example, here's a theorem that you got in Calculus 1, where it says a continuous function f of x has an absolute max, aka a global max, and an absolute min on any closed interval AB. Now this doesn't have the words if and then in the statement, but if we paraphrase this theorem a little bit, then we can rewrite it in the traditional if-then notation. We could say, for example, if f of x is continuous, then it has an absolute max and min on any closed interval AB. So the hypothesis, the thing that we need to be true in order to use the theorem, is that f of x has to be continuous. And the conclusion, the thing that we know as a result of applying the theorem, is that this function will achieve its absolute max and min on any closed interval. Now the thing that's tricky about theorems, that a lot of students get wrong when they're first starting to write mathematical arguments, is that unlike definitions, theorems are one-sided. If hypothesis is true, you can safely conclude that the conclusion is true. However, and this is really important, so we're going to write it in red. If the hypothesis is not satisfied, if condition A, the one after the word if, is not satisfied, then you cannot conclude anything at all. Cannot use theorem at all. You have no information whatsoever. To see some examples of someone using a theorem in an inappropriate and logically invalid way, let's look at a few concrete examples. Someone says to me, oh, okay, the street is wet, therefore it must have rained. Now clearly this person has in mind theorem number 1, which says if it's raining, then the street is wet. What they're trying to do is essentially use this theorem backward. The street is wet, so it must have rained. Of course, our personal experience shows that this may not necessarily be correct, because who knows, maybe someone was washing their car, maybe someone let their hose run wild, and that's why the street is wet. So this use of theorem 1 is not logically valid. And the problem is that this person has tried to reverse the roles of the conclusion and the hypothesis. The hypothesis, it is raining, is what allows you to use theorem 1 in the first place. If you don't know for sure that it's raining, you cannot use theorem 1, not at all. So this person swapped the if statement with the then statement. Similarly, we have an invalid use of a theorem here in this second example. Someone says, okay, I've got this function f of x equals 1 over x, and I know that it's not a continuous function. It has a discontinuity at x equals 0. Therefore, it must not have an absolute max or an absolute min on the interval 1, 3. Now this is definitely not true, because if we graph the function 1 over x on the interval 1, 3, then we can see that it actually does have an absolute max and an absolute min. But this person is trying to argue based on the theorem number 3 here, which says that if the function is continuous, then it must have an absolute max and min. They said to themselves, the function's not continuous, therefore it does not have an absolute max and min. But this use of theorem number 3 is also invalid, because the hypothesis of theorem 3 is not satisfied. Our function is not continuous. The hypothesis of theorem 3 is not satisfied. Therefore, even referring to theorem 3 in this situation is not appropriate. Theorem 3 is still locked and cannot be used. It cannot be used to make any conclusions whatsoever. We have no idea what's happening to this function based on theorem 3. Now here's the major takeaway. Over the next several days and over basically the entire front half of the course, we are going to be introducing definitions and theorems. Now these theorems and definitions are super important, and they should be written down word for word verbatim in the notes. You want to know exactly what the hypothesis of the theorem is, and you want to know exactly what the conclusion of the theorem is. Because if the hypothesis is not satisfied, that theorem is locked and you cannot use it in your argument at all. So let's get a little bit more practice identifying the hypothesis of a theorem and the conclusion. We have to be very, very good about this, because if the hypothesis is not satisfied, the theorem is useless to us. So, theorem number 1, if a number a is non-negative, then the nth root of a is a real number. The hypothesis comes directly after if. This is the condition that must be satisfied before the theorem becomes unlocked. And here, after the word then, is the conclusion. In that setting, you can safely and logically conclude that the nth root is a real number. Alright, next theorem. B squared is non-negative for any real number b. Now this is not written in the if-then format, but let's try and rewrite it so that the hypothesis and the conclusion are a little bit more clear. What this is saying is that if we have a real number b, then you know for sure that b squared is non-negative. So b is real is the hypothesis. B squared is non-negative is the conclusion. The nth root of a is a real number whenever n is an odd number. What condition must be satisfied? The condition that must be satisfied before we can say anything is that n is an odd number. If you know for sure that n is odd, then you can safely conclude that the nth root is real. So here's the hypothesis. An nth root is real is what you can conclude. And finally, every non-negative real number has a real square root. So in other words, if a number is non-negative and real, then that number's square root must also be real. The hypothesis is that the number is non-negative and a real number. The conclusion is that the square root must also be real. So be on the lookout for theorems which are stated in alternative formats. Alright, that concludes today's work. A little bit abstract, a little bit different than what you're probably used to. But understanding this idea, and in particular understanding the difference between a theorem and a definition, is critical for your success in the first half of the course. Definitions can be used in two ways. They can be used to classify things either as a term or not as the term. But theorems can only be used in one way. They can only be used when the hypothesis is true to state that the conclusion must also be true.